It's Monday, November 19th, 2012. I'm Rim.
I'm Scott.
And this is Geeknights. Tonight, we have a guest on the show who would probably like to introduce himself.
Hi, I'm Adam Becker, and I'm a freelance astrophysicist.
That is probably one of the more badass job titles I've ever heard.
Well, thank you. I made it up, so...
Let's do this. So, some of our listeners may know a person named Conrad who has been on the show once or twice before.
He's a character in Johnny Wander, and he's also a real person.
He is a real person.
I knew him when he looked like an 11-year-old boy.
I knew him when he was wearing a safety bucket that was dressed as Naruto.
Yes, he was inside of one of those highway safety barrels that itself was dressed up as Naruto.
But anyway, you might be wondering why we're talking about Conrad. You might think he's here. He's not here. Instead, he has sent a friend of his, a friend named Adam. What's up, Adam?
Hey, how's it going?
So we met Adam 15 minutes ago, maybe, and
we've done nothing but talk about embarrassing Conrad stories and teeth.
It's true.
So Adam seems pretty awesome, and we are going to do a show with him right now. So, Adam, why is it, for our listeners, I mean, I already know, why is it that you are so awesome and we would want you on the show?
I'm just a pretty cool guy, but I suspect that it has more to do with the fact that I am a freelance astrophysicist.
Wait. So when you were choosing a job back in the day, you decided to go for the dream instead of the money.
Pretty much, yeah. I mean, I actually did apply to become an astronaut.
Really?
Yes.
Don't you also have to be like a fighter pilot or something?
So there's the military track, but there's also the civilian track. And so they sent out a solicitation for applications, 9 months ago. And I looked at it and I said, okay, so I obviously don't meet the military track, but civilian track, check. Yeah, okay, I have the degrees and prerequisites. I can apply for this.
Yeah, but so I guess that didn't work.
No,
though.
It didn't work. I'm not in space right now.
Yeah.
But what I really want from that actually is the rejection letter. Because, how does every rejection letter start, right? It starts with, Dear Dr. Becker, we were very impressed with your qualifications, blah, 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 blah. And we felt that you were very, you were very well qualified for the position, but we found other people that suited our needs better. And so what I'm going to do is I'm going to take that letter, highlight the part that says you were very qualified for the position, and then frame it and say, see, NASA says that I am very well qualified to be an astronaut. I have it on NASA letterhead.
Well, one day when they make like a documentary about you, right, for the local news, for whatever reason it's going to be, which we can't guess yet, right? They'll have that letter will be part of the thing, like, rejected as an astronaut, but succeeded at this other awesome thing. Stupid NASA turned this guy down. They didn't know better.
Or it could be rejected as an astronaut and then the explosions.
Yes. Well, no, the explosions already happened. That would be a show about what I did in college. But, yeah, so I am a freelance astrophysicist. So
you're clearly way smarter than we are.
Well, I mean, no.
No?
I don't. Well, so I just met you guys. I don't know how smart you are.
Yeah, we don't know.
Not as smart as you.
Because this is Geeknights. What has Conrad told you about us? He sent you to a stranger's house.
Pretty much.
In Queens.
Yes, that's
and you
true.
showed up, and we had a bunch of video equipment.
So you trust him that much?
Not really.
How do you know we weren't going to, kidnap you?
So I only met Conrad 3 weeks ago.
Really?
Yes.
Okay.
So the story here is, you mentioned Johnny Wander. So Yuko draws Johnny Wander.
Yep.
And Yuko and I went to high school and middle school and elementary school together. We grew up in the same very tiny town in New Jersey. And
as we realized, Yuko is the Kevin Bacon of webcomics.
She basically is. But I'm, in that analogy, if Yuko's the Kevin Bacon of webcomics, then I'm a truck driver. Like, I'm not an actor in that analogy at all. But, yeah, so I know Yuko. And
do you know all those other people? Do you know George Rohack and no? Oh, okay.
No,
never mind.
What happened is I called up Yuko a few weeks back and said, "Hey, I'm going to be in New York City in October," and she said, "Oh, great, let's hang out." And we did, and I met Conrad and some of her other friends, and when I did, Conrad said, "Hey, you should be in podcasts."
Was he drunk at the time?
He was not drunk.
Whoa.
He might have been high on life.
When is he not high on life?
I mean, he's basically always high on life is my impression. But I mean, we had a good time. We hung out for an afternoon. And then he said, "You should be in podcasts. I have friends who do podcasts. When are you going to be in the city again?" And I said,
have a pretty good radio voice, despite just talking in your normal voice.
Thank you. Yeah.
I don't have to close mic you or anything weird.
That's awesome. Anyway, yeah. So he said you should contact them the next time you're in town. And I said, well, I'm in town next month.
And you actually did that? I
Well-
mean, a lot of times we'll meet people at conventions, we'll meet, all right, and we'll say, oh, you should do this, you should do that, but none of those things ever actually happen.
Right. So I'm a freelance astrophysicist. If I don't actually meet people, then I don't have a job.
Oh, okay.
Yeah.
Well, I'm sorry. I wish I could hire you for something.
No, don't worry about it. That's
but
not
maybe
what it's
somebody
about.
listening out there needs
It's
an
not about me.
astrophysicist.
It's not about me. It's about the science.
So let's talk about the science. So you're an astrophysicist, right?
Yeah.
I think the email though said you were a computational cosmologist.
Yes.
Right. So.
Yes.
And I guess there's also astronomer. So, you know, I sort of know the difference between those three things.
Okay, so so the story here is there's astronomy, there's astrophysics, there's cosmology.
Is there anything else I'm missing? Is there another one?
I mean, you know, there's
Astrology.
yeah,
That doesn't
so
count.
I was going to get to astrology in a moment.
We're well aware.
Yeah, so the general story is if you think that stars are small to medium-sized objects and that galaxies, you know, hundreds of thousands of light years across, or tens of thousands of light years across, are very big objects, then you're probably an astronomer or an astrophysicist. Whereas if you think that galaxies are very tiny, maybe point-sized objects, and the universe is very large, then you are probably a cosmologist. But the lines are fuzzy, and it's not wrong to call anybody in any of those fields an astrophysicist because that's sort of a blanket term. And the other thing is, outside of, you know, academia and conferences and whatnot, anyone who's an astronomer or a cosmologist or an astrophysicist usually self-identifies as an astrophysicist, because if you say that you're an astronomer, people will think you're an astrologer and ask you about their horoscope.
Oh, I mean, non-science people will think that.
Well, but if you say that you're a cosmologist, people will think you're a cosmetologist and start asking you about makeup.
Oh, okay.
I was going to make a joke about Cosmo.
Yeah, I mean, don't. Goodness, that's so
See,
clever.
I
You're the
was
first.
thinking, you know, if you were saying this, you know, I was assuming that you were going to identify yourself to a smart person and that you would say astrophysicist because that's more impressive, right? We tend to look at like the biggest people in science are astrophysicists, like the Stephen Hawkings and that, right? You know, so if you were just like an astronomer, that sort of, I guess, you know, seems like a not as prestigious word.
It's got physicist right there in the word, which leads to a lot less confusion. I guess it makes it sound more impressive, but mostly it's that if you say astrophysicist, people know that you are working with a lot of math and not with horoscopes.
Okay, so let's talk about the computational part of this.
Right. So basically what I
That's what we know about that.
Sure,
That's
yeah.
the part we know.
So in my research, what I do is, the one sentence explanation is I try to figure out how much we can learn about the way stuff was arranged in the very, very early universe by looking at the way stuff is arranged in the universe right now.
So like the distribution of galaxies.
Exactly.
Okay.
Distribution, like looking at the distribution of galaxies in the universe right now, or we're looking at what's called the cosmic microwave background radiation, which is the oldest light in the universe. But even though that's the oldest light in the universe, it's still from 400,000 years after the Big Bang, which is pretty good when you realize that we're now 13.8 billion years after the Big Bang. So that's, you know, pretty far back. But we want to know what the universe looked like a fraction of a second after the Big Bang.
All right, Hotshot. So where'd all the light go from that?
Where'd all the light go from?
Yeah.
Where was it between a fraction of a second?
I mean, you know, you had those. So there's the 400,000 year gap, right?
Right,
It's
yeah.
between 0 and the background radiation, right?
Right.
So was there just no light then?
The universe was opaque. The universe was not transparent. So, you know, right now we look up in the sky, we can see light. You can see with your naked eye light from the Andromeda galaxy. That's
Right.
2 million light years
because
away.
the vacuum of space is transparent.
Yeah,
Like,
the
light
vacuum of
goes-
space is transparent. There
Right.
might be some stuff in the way. You know, you might get some gas and dust, but on average, the universe is a pretty sparsely populated place. You know, the average number of atoms in a cubic meter of space is something on the order of a tenth of an atom. Is not very much. So anyway, but way back when, in the early days, the universe was not transparent to light because it was a lot hotter and denser because the universe was smaller. You know, the universe has been expanding, as you might know. It's been in a few papers, and so that means, you know, as things expand, they get cooler. So if you go back to the very, very early days, the universe was very, very hot and filled with, among other things, electrons and atomic nuclei because it was too hot for atoms to form. And so the thing about atoms is they're neutral, whereas the thing about electrons and atomic nuclei is they're not neutral. And so light interacts with them. Light will not just pass right through them or right by them. And so the universe was so dense and charged that light couldn't pass through it easily. And so light was sort of trapped for the first 400,000 years.
So any photons that any sort of reaction was emitting were absorbed or bouncing around and were not, you know, so they're all gone, you know, they're not flying around in space still.
Yeah.
I mean, I guess, like, what are the odds that, like, you know, a photon from then would have, like, you know, only bounced off things and somehow, you know, escaped and be able to be detected now, right? It's
I mean, those photons were trapped. I mean, talking about a photon bouncing around versus talking about a photon being absorbed and re-emitted is a little, that's a fuzzy distinction there. But those photons were trapped for 400,000 years. And then finally the universe expanded and cooled off enough for atoms to form, at which point the universe became transparent and the photons were freed. And at the time, they were in the infrared, but in the intervening 13.8 billion years, the universe has expanded so much that it has stretched that light out into the microwave. And so that's the cosmic microwave background radiation. If you've still got a TV with an antenna and you turn it to a dead channel, which I guess would be all of them now, and you turn the brightness way down, then about 1% of the little white specks that will show up on your screen come from the cosmic microwave background radiation.
So I don't think you're using a TV, though, for your research, right?
No.
You're using some kind of fancy telescope?
Yeah, I mean, that's how you find poltergeists.
Or something?
Yeah, TVs are how you find poltergeists. That's fair. Again, astrophysics, not astrology. So yeah, I'm not an observational cosmologist. I'm a computational cosmologist. So I don't look through telescopes. I don't build telescopes or satellites to collect data. I take the data and I crunch it with a computer. So the instrument that I use the most often, aside from, you know, pencil and paper, is a MacBook Pro. But the stuff that we use to collect the data these days is usually, well, for the cosmic microwave background radiation, our best data comes either from satellites that are way out in space. They're not even orbiting Earth. They're out at what's called a Lagrange point, so they don't get interference from Earth, and they take full sky pictures in the microwave range, or from ground-based surveys from, you know, really well-situated telescopes. Like there's a nice telescope at the South Pole that is taking really detailed pictures of the cosmic microwave background radiation. But the thing is, you can't get a full sky picture from the ground.
That's true.
And that's not so good. We need full sky pictures. We also need really detailed pictures of the sort that you can only get from the ground. So we need both. So I take that data and crunch it.
So what kind of software, like what kind of tool would you use to crunch? I mean, how much data even is that?
It's a lot.
Does it take a long time to download from the satellite in space?
I don't know how long it takes to download from the satellite in space. I mostly download it from websites.
That's a good idea.
Where they've already downloaded it from the satellite. So yeah, I don't know what the bandwidth of the connection out to a Lagrange point is. But yeah, basically, yeah, I get this data, and there are some pre-existing software packages that will crunch it for me somewhat. There's something called HealPix, which this is getting real technical.
How do you spell that?
HealPix, HealPix.
Okay.
So yeah, HealPix is basically a package for crunching this data. But it will only crunch it so far. It basically lets you display the data, and it also lets you do various simple transformations on it. It's also a format for taking the entire sky and basically pixelating it. because you've got something that's not flat. Now you need to display it as a set of pixels and deal with it. So how are you going to do that? So there's that. But then a lot of what I end up doing is writing code to do further analysis, because something like HealPix or some other software package that someone else wrote will only take you so far. If I want to do...
And it's also work that someone's already done.
Exactly.
So running the data through the same software someone else already wrote is going to get you the answer someone else has already found.
Essentially, yeah. So I want to do something fundamentally new. That means I have to, at the very least, take the results of that other person's software package and run it through my own software, which is a lot of what I do. So I write a lot of Python code.
I also write a lot of Python code.
Yeah,
Only
Python code is
much easier to write for me than for you.
There are some Python packages like NumPy and SciPy that make it a lot easier. And then when you want to actually write a paper, there's Matplotlib, which helps a lot as well. So yeah, I write a lot of Python code, and then I sometimes have to edit other people's C code, or on really bad days, I have to edit other people's Fortran code, which is sort of my least favorite thing in the world. Yeah, there's a software package that's written entirely in Fortran and has almost no comments, but it's also the best package of its kind. And sometimes it's easier to sort of modify that package rather than try to replicate it myself.
See, in cases like that, I always wonder, somebody could just go in and line by line translate it to some other language, even if it doesn't, even if it's Fortran's not object oriented, but it's you can write non-object oriented Python, right? You can just go through.
Well, actually, frighteningly, there is a way to do object oriented Fortran, and I wish I didn't know that. But
I did not know
that. Yeah, you could do that if you had a lot of time and nothing better to do, which I can't imagine anyone in the world.
Scott, that's the thing that some people might do or believe.
There are people.
Yeah, I suppose that's true.
So what kinds of things do you look for? What's something you recently, you're crunching this data, and we're talking in very high levels right now, but what's the kind of thing you're actually looking for or trying to find?
Well, okay, so...
Or trying to prove, or whatever it is you're going for.
Yeah, so going back to that one sentence description, I look for stuff in the universe right now to try to figure out what the universe looked like right after the Big Bang. Specifically, the stuff I end up looking for, it's not like I'm looking for a particular galaxy cluster. The laws that govern the universe at this level are mostly statistical. So what I end up looking for are statistical quantities. So specifically, what I've been looking for lately, and now I guess this gets slightly technical. There's a question.
Technical as you want.
Yeah. Okay. Fine. So there's the question of how. You know what? No, I'm going to back up for a second. The theory of general relativity from Albert Einstein describes the universe on the very largest scales. And it also just tells us how gravity works on smaller scales, but we can use it to describe the universe on largest scales.
Right.
And there's a set of equations that go along with general relativity, and you can sort of basically put in the universe that you have, or put in certain conditions about the universe, and those equations will pop out a solution which describes where you live. And to describe the universe on the very largest scales, we usually punch into those equations the assumptions that the universe is what's called isotropic and homogeneous. So it looks the same in all directions everywhere. And on very large scales, this is an extremely good assumption. If you take a picture of the universe on really large scales, it's kind of smooth. The universe looks the same everywhere. The problem is that's certainly not true at small scales. Otherwise, we wouldn't be here. And remember, I said the universe is pretty sparsely populated. Well, not here. We have a lot more atoms here per cubic meter than you do out in intergalactic space.
So in any given direction, the cosmic background radiation is uniform, but then close up, there's a galaxy here and there isn't one mirrored on the other side.
Exactly. And even the cosmic microwave background radiation, it's not actually uniform in all directions. It has tiny little variations. And so that's interesting because the variations we have now are not tiny. The variations we have now are huge. It's not a fraction of an atom per cubic meter here. It's something like 10 to the 23 or more atoms per cubic meter here. Whereas if you go and look at the cosmic microwave background radiation, you see differences, but those differences are like 1 part in 10,000.
So, but is that like, is that 1 part in 10,000 like an echo of back then there was a huge lump in a place which causes a very small lump now? Or
no,
like how does it correlate? Like if you see that in the background radiation now, what does that tell you about what was there then?
It tells you that what was there then was a piece of the universe that was slightly more or less lumpy to the tune of 1 part in about 100,000. The relationship is proportional. So the question is, how do we get from these tiny little lumps to the incredibly lumpy universe we live in now? The answer to that turns out to be pretty easy to understand. It's just gravity. If you just throw gravity into a slightly lumpy universe and let that universe evolve for 13.8 billion years, what's going to happen is the slightly denser places will attract more matter, and the slightly less dense places will have matter fall away from them. And eventually, after a few billion years, you end up with stars, galaxies, galaxy clusters.
All right, but that puts us to an earlier order question then of where did that original slight lumpiness come from?
And that's exactly it.
Well, is it a false assumption that it was originally perfectly smooth, or was there,
Well, so those are active research questions.
All right.
That's essentially what I work on.
Man, you scientists never have any answers.
Well, so we have, actually the real problem is we have too many and we don't know which one's right. We have many different theories about where those
what are like 3 or 4 of the a few of the like big ones that are getting a lot of that people seem to think are right and aren't crazy kooks.
So there's one big one. Okay. There's one really big one. And this is something called inflation.
Okay.
And the basic idea is, in the very early universe, the very, very early universe, a fraction of a second, a billionth of a billionth of a billionth of a second after the Big Bang, there was a brief period where the universe expanded very, very rapidly. Expanded something like 10 to the 50 times. So it expanded by a factor of a 1 with 50 zeros after it. Something like that. So, sorry, it might be a 1 with 20 zeros after it, but it doesn't really matter.
It doesn't really matter. The point is that there are a lot of zeros in less
than a second. A lot of zeros, yeah. So the point is, for a very, very brief fraction of a second, the universe expanded a hell of a lot, and then that stopped. And it continued to expand after that, just not nearly as quickly. So the interesting thing here is what that would do. That does a lot of things and solves a lot of problems and brings up other problems. But what that does for this question of where did the original tiny lumpiness come from, is it says, quantum mechanics is the set of rules that govern the universe on really tiny scales. And quantum mechanics says that sometimes crap just happens. Quantum mechanics is what we call fundamentally stochastic. There's randomness in the universe at a very low level. So if we were looking at something really tiny and we saw tiny differences all over the place, we'd say, well, we don't really need an explanation for that. That can be explained just by the nature of quantum mechanics. So what inflation says is, so there were these tiny differences, but then the universe expanded so rapidly that those tiny differences got expanded up and turned into tiny differences on a macroscopic scale, on a scale bigger than the scales that quantum mechanics really deals with. And so they kind of got frozen in. So basically, and this is a direct quote from now I'm going to forget
someone
who said
famous.
it. But someone famous said that basically these tiny little differences in the cosmic microwave background radiation are quantum mechanics writ large on the sky. So that is a very popular theory in inflation for explaining this. There is one problem, which is, two problems. The first is what drove that period of rapid inflation? And second, which inflation? Because it turns out that if you try to answer the first question, you can answer it in dozens and dozens and dozens of different ways. And that's it's difficult to distinguish between those different theories of inflation, because we're talking about a period in the universe's history that is not only before the oldest light, but also before the oldest atoms. Atomic nuclei were formed in the universe between 3 and 20 minutes after the Big Bang. So it's older than anything that has survived until the current time, except for those tiny fluctuations themselves. So by studying the way stuff is arranged in the universe right now, we can learn more about the distribution of those tiny fluctuations, and thereby hopefully learn more about what kind of inflation happened, or if inflation happened at all.
This is a joke for Rim. It's the darkness that came before.
I have no idea.
I
what
know you're
talking
not supposed
about.
to get that joke. No,
It's okay.
That's okay.
We argue a lot about the nature of, well, not necessarily free will, but causality, in the sense that you're basically what you've said from this theory is that quantum mechanics, effectively, if you zoom in far enough, things are random. We don't know or care why. Or if we do care, that's a separate field of inquiry.
I think the second one is where I'm going to go with that, because I care very much. So, other people may not. But
That
yeah.
it's a question that, for the purpose of discussion, most scientists will say when talking about these other things, we don't know why, and that's separate.
Yes, it is. It is certain. We don't. It is separate. Some people say that we do know why. Other people say that we don't. There's a whole field called Foundations of Quantum Mechanics, which deals with this kind of thing, but it's not relevant.
So it would
us.
imply that on the macro scale, that things happen in a deterministic fashion, in the sense that we can predict, gravity and all these things. We can theoretically predict how macro bodies will react to events, and they'll always react to the exact same event in the exact same way.
Kind of.
Or is it that they won't because we can't perfectly recreate, or is it that they won't because those tiny fluctuations we're ignoring actually make it impossible for the same thing to happen twice?
So, yes, is essentially the answer to your question. Let me give you.
He's trying to ask philosophy questions.
Yeah, no, asking philosophy questions is fine.
No, but in a very direct, I only want the physics answer.
Okay, well, so first of all, to toot my own horn a little bit more, I actually do have a degree in philosophy.
Oh,
Yeah, fancy. No, I did my undergrad.
he's got a whole bucket full of horns here.
It's
to
true.
chew.
Yeah, I did my undergrad in philosophy and in physics. So it's a bachelor's degree, which but
That's all I've
I
got.
have one of those.
No, I'm not belittling.
Only got
that.
one horn.
Wait, he gets to wear the octagon hat. I only get to wear the square hat.
Oh God, no! I didn't wear any hat. Those hats are expensive.
Really?
Yeah, they're really
I
expensive.
didn't even pay for one. Rim just grabbed one for free. I didn't even go to the
No, the
graduation.
octagon hats are expensive. My parents said, "So are you going to walk for graduation when you get your PhD?" And I said, "No."
Well, I guess when you're only freelance astrophysicist,
Yeah,
they don't give you the free hat.
Well, Scott, he has to pay like 10 talents to.
No. I do not have to pay 10 talents in order to get back into the School of Magic.
Okay, so you've read that.
Anyway.
That was just
you got one fantasy joke out of 10.
that was
Yeah.
just the Geeknights book club book.
Sorry, yes. See, and I was trying to remember the name, and I forgot. Anyway, right. Where were we?
I don't remember.
I don't. Oh, right. The hats are expensive.
Causality.
Causality. Right.
How come if we do the exact same macro event, the exact same result
this
does not
is,
always happen?
In the grand tradition of physics problems that you probably remember from high school, this is a slightly idealized setup, but really only slightly. Imagine that you have the perfect pencil. And when I say you have the perfect pencil, I mean you have a pencil that comes to, an atomic point at the bottom, which is actually not a terrible assumption because graphite's pretty interesting as the things go.
Yeah.
But
So we're talking like it is one Planck,
So
width
it's
at
basically
the
as
end?
sharp as a thing could be, right?
as sharp as a thing made
There's
of atoms
one
can
atom
be.
at the end of
Yeah.
it, and all of the other atoms are sort of behind that one
Exactly.
atom.
So
right?
no, not one Planck length.
Okay.
That's a hell of a lot smaller.
That's
but,
what I was saying. I've not made like some sort of
Yeah,
quark knife.
it's not a neutrino
No.
at the bottom, right?
It's not a subtle
it's
knife.
an atom.
No,
Right.
it's
Scott has not read the Golden Compass.
okay. I'm sorry. Anyway, no, it's not.
So we're at the same fantasy score now.
Yeah, there we go. So it's but it's an atomically perfect pencil. Okay.
Okay.
So this thing is standing. Okay, you have it standing on its point.
Oh, it's not standing on the eraser.
It's not standing on the eraser.
That'd be a
it's
lot
standing on its
easier.
points. That would be a lot easier.
So what's it standing on? Is there another atom?
No, I mean it's standing on a table.
Okay.
Right. Okay.
So what atoms?
Anyway,
are-
this is the idea. Classically, if you do Newton's laws of motion, you can say, okay, yeah, well, this is what we call an unstable equilibrium. If you tip it slightly in either direction, or if it's moving slightly in either direction when you let go of it, it's going to fall over. But if you can get it to just not move and get it perfectly straight up and down, in theory, it'll just stay there forever.
If there's no wind and
if
no
there's
table
no wind
shaking,
or anything like that,
right?
yeah. But pretend there is no wind and there's no table shaking, and it's just somehow in this perfect room on Earth there is gravity.
And but the entire pencil itself would also have to be perfectly uniform,
Right,
with the
that'd be
same
perfect.
number
He
of
said it was a
atoms
perfect
and- right.
pencil.
Perfect
That was
pencil.
like the first assumption.
And
that part.
the gravitational field in the
Right.
room would have to be perfectly uniform. Anyway, say that all of that's true, but Newtonian physics would then say if you somehow did that, the pencil should stand up forever. But quantum mechanics says otherwise. Quantum mechanics says, well, you can't do that, because in order to get the pencil to stand straight up and stay there, you have to get the top of the pencil sitting directly over the bottom of the pencil, and you have to, when you let go of it, not only have that in the right position, but you have to not impart any momentum to it. You have to not have it be moving. And Heisenberg's uncertainty principle says that you cannot know the position and the momentum of something with perfect accuracy.
Oh, so you can only do one or the other.
You can do one or the other, or you can compromise on both. So the question is, if you compromise on both, which turns out to be the best thing, what's the maximum amount of time that you can get this perfect pencil to stand straight up? So what's the quantum mechanical limit on how long the pencil can stand straight up? Do you guys want to guess?
So as soon as the pencil leans a little bit, time's up.
Well, no, it's not time's up. It's how long is it going to take for the pencil to go from here to like here? On appreciable fraction away from straight up.
This is the perfect pencil.
This is the perfect pencil.
And you did the best job you could.
You did the best job physically possible. And this is the question of, okay, so what impact does quantum mechanics have on what is, frankly, a really big pencil?
All right, well, I'm trying to imagine how long it takes for a regular pencil to fall over.
I'm going to say something ridiculous. I don't know, 10 to the 6 years.
Okay.
Oh, you're saying a really long time, Rim?
Yeah, I'm saying a really long time, but it'll eventually happen.
Right. And I mean, so this is a reasonable guess, right? Because quantum
Booyah!
mechanics.
Yeah.
Yeah, this is a reasonable guess because quantum mechanics, should take a while to affect something giant like that. But you're actually totally wrong.
Yeah, I was waiting for you to say but.
Yeah, I was gonna guess about the same time it takes for a regular pencil.
That's
to fall
actually
over.
about right. It's 4 seconds.
Okay.
So see, listeners, that's why the pre-hawk is dangerous.
So yeah, if it doesn't matter how long you want to balance your pencil for, you're not going to do it for more than 4 seconds, unless, of course, you don't have the perfect pencil. If your pencil's not sharp enough, all of this goes out the window. But the point is, quantum mechanics can actually affect initial conditions in life enough to introduce an element of quantum mechanical random crap into your setup, and so things won't be deterministic.
So there's no causality and stuff just happens, and we can correlate. It sounds like.
So even if you want to say that means that we don't have a way of understanding causality at the quantum mechanical level, and now we're getting into foundations of quantum mechanics, and you don't really want to do that here.
All right, so we don't want to do that. Let's go to another physical topic, and then we will go into non-physical topics.
I thought you were about to say let's go to another caller.
No. Okay, so we have a friend Timo who actually he lives in Finland,
And he's on the phone right now?
No, he's not. He's more of like a particle physicist and such,
yeah.
right? So
Yeah.
as someone who is not, I see physics, and I see the kind of work they do with like finding Higgs bosons and stuff, and then I see outer space stuff, but I really don't see a lot of connection between the two, right? So is there one, and if so, what is it?
There's definitely a connection.
I imagine there was.
Yes. So here's the basic idea. There's 2 ways to talk about that. We'll talk about both of them. So the first thing is, the universe is a pretty big place right now. Okay,
in relation to what?
In relation to me.
Oh, okay,
That's
never mind.
enough.
in relation to any object you have ever seen in your life, including the Andromeda Galaxy. So, yeah, the universe is a pretty big place, but it wasn't always so, right? The universe is expanding. So if you go farther back, like we said, eventually the universe is opaque. The universe is hotter and denser. If you go way back, eventually the universe is as hot and as dense as the stuff that you produce in a particle accelerator. And in fact, the Big Bang has been called the poor man's particle accelerator. Because stuff happened there that has not really happened since, except in particle accelerators.
Oh, so the thing is, like, I imagine the Big Bang would be hotter and denser, way more than we could possibly,
yeah. So the further
But you're
back
saying
you
it's,
go,
it's as hot and
well,
as dense.
at some point it is, and then if you go farther back than that, it's hotter and denser.
Oh, okay.
And so the better the particle accelerator we get, we can also, the farther back in time we can probe. So, the same way that telescopes are time machines, because the farther away you look, the more ancient the light. Particle accelerators can also be time machines, because the hotter and more energetic you get your collisions to be, the farther back in time in the universe's history you have successfully simulated.
There's no danger, though, of like a universe just being created suddenly on Earth, right?
No.
No, I didn't think so.
No. The energy scales necessary to do something like that, well, if you make a bunch of assumptions about how that might work that are very charitable to us and our abilities, you still don't get anywhere close.
Okay.
There's such a thing as observational cosmology, but there's no such thing as experimental cosmology, as much as we might wish otherwise. So, yeah, so that's the first answer, is they're sort of connected in that way, and that, particle accelerators can tell us what the very, very, very early universe looked like. But there's also another way in which they're connected, and this is pretty cool. So there's this wonderful theory called the Standard Model
I've heard of
particle physics. Yeah, it's arguably the most successful scientific theory of all time by some measures. It's extremely accurate. It successfully describes basically everything that we have ever seen, with four notable exceptions, and I'll get to those in a second. But it describes every interaction we've ever seen at a particle accelerator, and even this new Higgs boson result is starting to look like it falls in line with the Standard Model, which is, frankly, bad news. And I'll explain that in a second. We're all hoping that it doesn't fall in line. Because the thing is, we know and have known since the Standard Model was cooked up in the 60s and 70s that it has to be wrong, or at least incomplete. Because one of those four things, when the Standard Model was put together, we didn't know about four things that didn't fit. We only knew about one thing that didn't fit.
Gravity?
But that one thing is gravity.
Yeah.
Right.
So
How come the one that's the easiest for me to mess with and understand at the macro level doesn't make sense at any other level?
So here's an interesting thing. Gravity is special because of two things. It's, well, more than two things, but two things right now. It's the weakest force by far. And it's also, there's no such thing as a gravitationally neutral object. Okay? You can put together a positive and negative electric charge and get something that has no electric charge, but you can't do that with gravity. So, early on in the history of the universe, the other forces, the strong force and electromagnetism, not so much the weak nuclear force, which is a different story. But anyway, the strong force and the electromagnetic force sort of took their turns creating structures that were neutral with respect to those forces. Okay, so, electromagnetism got electrons and nuclei together, made atoms. Atoms are electrically neutral. Electromagnetism said, okay, I'm essentially done. Electromagnetism still plays a huge role in the universe today, but on large scales, the universe is mostly electrically neutral. And the strong nuclear force did the same thing when, atomic nuclei were put together. But gravity can't do that. And gravity also sort of had the last turn because it's the weakest one. And so
after everything else was neutralized, the electric force is neutralized, the strong nuclear force is neutralized.
But we still have lumps.
So now you're sitting there, you're some neutral object, matter, whatever, but gravity is now affecting you.
Exactly.
Right?
And
there isn't some strong nuclear force pulling you away from gravity so that the gravity doesn't matter as much.
Precisely. Yeah. So gravity, as a result, governs a lot of what we see in the universe on large scales, and also a lot of what we see on these sort of intermediate scales where we live, simply because we're living on a big thing. But if you want a demonstration of gravity being really weak, you've got that whiteboard over there with magnets on it. So those tiny magnets are being held up by magnetism, okay, against the entire gravitational pull of the Earth. So those really, really small magnets And those magnets aren't even using sort of the full strength of electromagnetism because there's
They're pretty weak magnets.
They're pretty weak magnets, and they're
I have
also
some shitty ones that fall off the fridge.
they're also dipoles. They've got both a north and south pole. This means that they're not actually going to be as strong as if you had, say, a positive and negative electric charge. I mean, you could levitate a building pretty easily if you put a bunch of positive charges on the floor and a bunch of positive charges on the building. I mean, it would then fall over. It's not going to be stable that way.
So it's a big pencil again. But
yeah, exactly. Yes. But nonetheless, it's really easy to counteract gravity with any of the other forces. But yeah, gravity, why gravity is sort of messed up and doesn't fit in. The best analogy I ever heard about this is basically the standard model tells you how the players act on the stage. The problem with gravity is gravity comes in and warps the stage. Gravity is a set of rules for how the stage behaves, not the players. Because, you know, gravity, as general relativity tells us, is a warping of space-time. So, yeah, so we knew that the standard model wasn't complete. And since then, we've discovered several things that don't fit in with the standard model. 3 other things, like I said, 4 things total. One of those things is dark matter. There's nothing in the standard model that can account for dark matter. And another thing is dark energy, which is causing the expansion of the universe to accelerate rather than slow down over time. And this has, we don't know as much about dark energy as we know about dark matter, but assuming that we're not just wrong about gravity, something is causing this. And there's nothing for that in the standard model either. And then there's the last thing is this thing called neutrino oscillation. Basically, the standard model says that neutrinos shouldn't have mass, but we know that we now have evidence that neutrinos do have mass. And it's a small mass, very small, but the standard model can't account for that. So these 4 things, gravity, dark energy, dark matter, neutrino oscillation, they don't fit in the standard model. And even if you're skeptical about dark energy and you say, no, dark energy is just that we don't understand how gravity works on really big scales, the other 3 are pretty solid. And certainly we know that gravity is real. And we've seen neutrino oscillation in the lab, and the evidence for dark matter is pretty good too. So none of those are explained by the standard model. If we can come up with something that breaks the standard model, if we see some evidence in a particle accelerator of something that is not accounted for by the standard model, that would give us hints of the next theory. And that next theory could account for dark matter and dark energy, which are 2 of the biggest outstanding questions in cosmology. And so this is a connection between particle physics and cosmology.
No, look at that. Look at how you remembered what he was talking about the whole time.
Wow, I don't think I've ever done that in my life.
Yeah, I tend to go out. It's like you were going tangents, but you remembered where you came from. That was really. I go on tangents, and then I'm like, what was I talking about?
You return to the darkness.
Well, I go on the most tangents.
Yeah, well, I mean, politicians should learn something. Actually, answering the question. It's crazy.
Well, yeah, I don't think it's that they can't. I think it's that they
don't want to. Yeah.
So we'll get into some So my last question before we get into the sort of non-science personal stuff. How does one who is in, say, entering high school decide to do what you do and actually make progress toward that?
So, I mean, I wanted to do some flavor of astronomy since I was in 1st grade.
Yeah.
I mean, I sort of fell in love with astronomy. I read some books. I sort of went out and saw the night sky because I was in Jersey, so you can see the night sky.
Can't see shit here.
Well, you can see Jupiter here.
That's
I
about
actually
it.
saw Jupiter from Brooklyn last night. Look to the east after sunset. Anyway, yeah, I mean, you can totally see a few things here. But yeah, I mean, you looked at the night sky. I saw Cosmos, Carl Sagan.
Yep.
Amazing stuff. And I got really into it. And I mean, and then I sort of waffled a bit as I got older, but I was always sort of, hooked on the idea of, okay, I at the very least want to do physics, and I do really like the sky. So yeah, I mean, there's not a whole lot that you can do before you get to high school, aside from, read a bunch of books if you're interested. Once you get to high school, take science and math as much as you can.
Get A's.
Do as well as you can. And when you go to college, major in physics or astronomy.
What would be the difference? I mean, what would be the difference between the 2 majors?
It depends. At some schools, there's very little. Usually what happens is a physics major will give you some flexibility with some of the courses you take. There's like a core and then some physics electives. Generally, an astronomy major, this is how it worked where I went to school, will usually be the physics major, but they pick the electives for you, and then there might be a couple of other courses on top of that, so it's sort of more specific. Because, you know, physics as a major is pretty versatile. You can do a lot of different things with it. You can go into physics education. You can go and work on Wall Street. You can go and work for Google. You can go do a lot of different things with a physics major. I mean, you can go into patent law.
Unlike a philosophy major?
Yeah. I had a choice between physics and philosophy for graduate school, and one of the reasons that I chose physics was that, fair or not, and I don't think it is fair, you can do more with a advanced degree in physics and an advanced degree in philosophy. But yeah, so major in physics or astronomy, and then go to graduate school. I mean, if you want to make research contributions to the field, it's very, very difficult to do that without a PhD. If you want to make contributions to observational astronomy, that you can do without a PhD. You just need to get a really good telescope and become very familiar with the night sky, and you could easily discover an asteroid or a comet or something like that. But if you want to make research contributions to our theories of how the universe works and where it came from, you kind of need to get a PhD. And then once you do that, you have a few options. The traditional academic path after a PhD is to go for what's called a postdoctoral fellowship, and I've applied for a few of those and I'm waiting to hear back. There are also a few other avenues that you can take. I mean, I'm freelancing right now. That's partly because of the way the timing worked out, partly because I need a little bit of a vacation, but also,
I need one of those.
Yeah, but also partly because I wanted to see if it could be done. I mean, the current academic model, its days are numbered. Everyone agrees on that. They just don't agree on what's coming next.
Yep.
And so I figured, well, I can try to stake out a position outside of the current model and see what's coming next. But I'm hedging my bets. I'm also applying for postdoctoral fellowships. Yep. So we'll see. I mean, the other thing is, and this is not new, this is actually quite old in a sense. If you have a PhD in the field, and you end up being supported doing something else, like if you have a job working for a tech company or something like that, if you somehow have the time and the connections, and this is easier now with the internet than it was, say, 50 years ago, you can still do research on the side. It's just that research is something that takes so much mental energy and so much time that it's difficult to do it it's difficult to do it while doing something else, unless you really make time for it very carefully. Like if it is part of your professional life, but not the entirety, that's fine. There are people who split their time between research and education, but it's difficult if you have a full-time job doing something that is entirely not research to also do research. I mean, I'm still doing research, but that's because I'm freelancing. So it is part of my professional life.
All right. So I think we've taken enough of your time. You have to get back to science things. So on a personal note, you know, to get a little feel for you and like what you do outside, you know, as a geek or nerd or scientist or whatever.
This is a show about nerdinism.
Absolutely.
It's not entirely a science show. So
sure, yeah.
So you've already expressed that you're a board game person.
Yeah, I do like some board and card games. Yeah.
What's like your favorites board games? You know, do you play to win? Are you super serious or?
I have trouble taking myself seriously. Okay. So no, I mean. No, I guess I play to win in that sometimes I play and then I win. But no, I don't. I really like Settlers. Settlers is good.
So the problem with Settlers is that it's pretty solvable and the game is random, but once all players have equal
wouldn't
maximal
you know that,
skill.
Mr. Smarty?
No, actually, I never looked that up. I guess that makes sense, but it takes the fun out of it.
It does.
Well, so
you are correct.
I mean, it's
does
not like
astrophysics
shoots and
take
ladders, right?
It seems like so fundamentally, all games are either solvable or random, and there's no other
rock,
kind
paper,
of game.
scissors.
Yeah.
Well, yeah, but that's psychology.
All right. So
movies. What do you like? What kinds of movies do you like? I can't name like a movie that's like one of your favorite movies.
Groundhog Day.
Yeah, it's a good
All
one.
right.
I like that.
Groundhog Day is one of these movies where. and I'm not joking, if you watch it a few times over, it really grows on you. It's it's easy to sort of write it off as this sort of light comedy, but it actually is an extremely it's a deep movie. There's a lot there, but it's also a lot of fun. Like it's not I wouldn't say that's the best movie ever made, but it is easily one of my favorite movies, if not my favorite movie.
No.
It's definitely way up there for me too.
Yeah.
So you clearly read The Name of the Wind.
Yeah.
I did read The Name of the Wind. That's true.
What other books?
Yeah,
have
like
you
what
read?
other-
Wise Man's Fear.
Okay. I haven't read that yet. It's sitting
you
there.
So I
should.
guess my question there, just very briefly, because
Yeah.
we just did a whole Geek Nights book club on it. And
Yeah.
we put our opinions out on the internet.
Yeah.
What did you like that book?
Yeah.
And are there fantasy books or other books you like more than it?
I mean, so I'm a big Ursula K. Le Guin jumper.
Right?
Me
So,
too. Me too.
I'd say that A Wizard of Earthsea and those books are really, really good.
Also a previous book club selection.
Yeah.
Have you read The Dispossessed?
I have read The Dispossessed.
I like
That's
that
an
one.
incredible book.
I love that book.
So you
Yeah.
probably haven't read The Prince of Nothing.
No.
that's
I
the
think-
R.
joke.
Scott
That's the joke
Becker.
you missed.
It's R. Scott Becker. It's basically philosophy, punk, gritty science fiction.
It's on your list
fantasy.
now.
Okay.
You're reading
Based
it.
on the discussion we just had, it's probably up your alley.
Awesome. Okay. Yeah.
What else we got here?
I don't know.
You said that you swore off video games in the school days.
I mean, I did break that promise for 2 short video games, but yeah, I in college and grad school. Well, in college I didn't play any video games because I wouldn't have made it through, and it was difficult to make it through.
You chose much better than a friend of ours.
I did actually. I did play one video game in college one night. I found myself with literally nothing to do. It happened exactly once in college, and I went to a friend of mine and said this. He said, "Oh, you have nothing to do? Here, play Civ."
Which Civ was that?
I think it was Civ 3. And
Ah.
I went back to him 10 hours later. So like I had this conversation with him at 8 at night. I went back to him 10 or 12 hours later and said, "Hey, so I haven't slept. Take this away from me and don't give it back."
Yeah, that was probably
So
wise.
yeah, so I'm not.
That was even the bad Civ.
Yeah, I have difficulty with that kind of control. So I just didn't do that. And
It's a good thing you've stayed away from the MMOs then.
Yeah, exactly.
No, forget
I
that.
won't
Never
play them.
Google a thing called Europa Universalis. It's
Yeah.
it's a Europe simulator.
I will not play MMOs. I won't
Yeah.
do it.
That's a good move.
So I mean, it's not that they're not fun. It's not that they might even for some people in some ways be a valuable use of time. Somebody just got concrete poured on him over there.
Awesome.
Sorry.
yeah, they're building another tower of the
Yeah.
Geek Night studio.
Anyway.
So Star
so-
Trek. Do you like Star Trek?
Oh God, yes.
All right, Picard. Well, who's your favorite captain? Scott hates Star Trek, so
Oh God, Picard's awesome. I mean, so I have a really soft spot for Picard because I grew up with The Next Generation. You know, it was
Yep.
what was on TV when I was a kid.
yep. And then Deep
So-
Space Nine was on after, and I'd fall asleep.
Yeah, and Deep Space Nine is good. The thing is, and this is where I lose some nerd cred, Deep Space Nine has continuity. You have to watch the whole thing all the way through. I haven't. I have started to, and I really like it. And I am open to the possibility that Cisco might in some ways be better than Picard. Because, you know, Next Generation has some continuity. It doesn't have none. It just doesn't have nearly as much as Deep Space Nine.
Yeah.
I mean, I do feel like it's a shame that the original series movies have always been way, way better than the Next Generation movies. There's really only maybe one Next Generation movie that's any good. So that sucks. I was also way more into Star Trek when I was younger. It's sort of one of those things which I feel like I did. And now it's like, okay, yeah, I have some Star Trek knowledge, but it's not something that's been a big part of my life.
That is a weird thing to think about, right? Because, like, I don't like Star Trek, but it's like I see like a lot of people now are sort of picking it up later,
Yeah.
versus other people who picked it up earlier, and it's
Yeah.
sort of like almost like two different groups of fans.
Yeah,
you know, it's like
it
the people who
is.
picked it up early in life are like the Trekker, whatever
Yeah.
word is the correct word for them. You know, people.
You'll
whereas-
piss off half of them no matter what you
Sure.
say.
And
Yeah.
then, you know, the people who are like, you know, 20s, 30s now watching it on Netflix and stuff who are, you know, still huge fans of it are sort of separated from them in a way, even though
Yeah.
they're fans of the same thing.
Well, we see that. Look at My Little Pony and the people who are fans of it now going to
Sure.
the My Little Pony conventions and just
But
horrifying.
that's a different
Yeah.
show. These are the same exact shows,
I
which
mean-
is why it's sort of, I think, a unique case.
Yeah, my feeling about Star Trek for me in my life is just that it's almost a little like Ninja Turtles. I was really into Ninja Turtles when I was a kid, and then
Ninja
you know
Turtles.
I was done. and I wasn't
I'm
really into
also
them. And,
mostly done.
And now, yeah, I like Ninja Turtles.
Yeah.
I'll go see, I went to see that Ninja Turtle movie that came out a few years ago. But
What?
yeah.
I did not know about this.
Yeah,
Okay.
I mean, and it was fun. Okay. But it's not like I own massive quantities of Ninja Turtle or Star Trek paraphernalia. I don't live or die or breathe the stuff.
Is there anything you do live or die or breathe?
Other than science?
Other than science?
Doctor Who. I really, and that's because I came to it late in life. Like basically, what happened was in grad school. I keep saying in grad school. A couple of years ago, my girlfriend came to me and said, "Hey, so I just started watching this show, and you need to watch it. You need to watch it. What's it called? Doctor Who? Oh, I've vaguely heard of it. People seem to get really into it. Yeah, let me just sit down and watch it with me." Okay, fine. And then after watching a couple of episodes, it is sort of, okay, this is kind of the best thing ever. I mean, have you ever... Another thing I've gotten really into is Community. Do you guys watch that?
I've seen a few episodes.
Scott, he doesn't watch or like most things.
There's this wonderful scene. So Community has its own takeoff on Doctor Who, right? Inspector Spacetime. And there's this wonderful scene where Abed sees Inspector Spacetime for the first time, and he's watching this incredibly cheesy clip, and he watches about a minute of it, and then he says, "This is the best thing I've ever seen in my life." And that's essentially what happened to me.
Guy at my work, Halloween costume was Inspector Spacetime.
Yeah. Well,
so there you go.
Yeah.
Yeah, there's a lot of Who people out there.
Yeah, there really are.
We go to conventions and it's like it's everywhere. It's
Last
insane.
year for Halloween, before I'd finished my degree, I dressed up as the doctoral candidate. So the young doctor.
Clever girl.
Yeah, maybe. I'm trying to think if there's anything else that you guys. I have a website.
Oh yeah.
Yeah,
Is there anything else that you would like to pimp?
Yes. Now is the
yourself?
pimp and plug yourself, independent of the opening to this.
And also, if there's anything else you would like to tell an audience of some number of nerds.
Well, I've got a blog, and it's called Freelance Astrophysicist, and it's at freelanceastro.com. So yeah, if you want to read more of my stuff or hear more about what I'm up to, you should go there. And you can also, if you have any questions about science that you want to ask me, you can send me a question through the site, and it might take me a little while to respond, but I will respond. Anything else?
I could end it right there.
Yeah, you can, I mean, yeah. I don't have any other personal projects. I mean, if you know someone in San Francisco who's looking for a math or science tutor, I have some openings.
We can do that.
And yeah, beyond that, I think that's all I've got.
All right.
Well, thank you for taking the time to come to our somewhat disheveled studio right
yeah,
now.
that show was particularly awesome, and I'm sure it'll be enjoyed by many.
This has been Geek Nights with Rim and Scott. Special thanks to DJ Pretzel for the opening music, Kat Lee for web design, and Brando K for the logos.
Be sure to visit our website at frontrowcrew.com for show notes, discussion, news, and more.
Remember, Geek Nights is not one, but 4 different shows. Sci-Tech Mondays, Gaming Tuesdays, Anime Comic Wednesdays, and Indiscriminate Thursdays.
Geeknights is distributed under a Creative Commons Attribution 3.0 license. Geeknights is recorded live with no studio and no audience. But unlike those other late shows, it's actually recorded at night.
Well, I mean, no.
No,
I don't. Well, so I just met you guys. I don't know how smart you are.
Yeah, we don't know. What do you,
not as smart as you.
this, because this is Geeknights. What has Conrad told you about us? He sent you to a stranger's house.
Pretty much.
In Queens.
Yes,
and
that's
you
true.
showed up, and we had a bunch of video
So you
equipment set
trust
up.
him that much?
Not really.
How do you know we weren't gonna like kidnap
So
you?
I only met Conrad 3 weeks ago.
Really?
Yes.
Okay.
So the story here is, well, you mentioned Johnny Wander. So Yuko draws Johnny Wander.
Yep.
And Yuko and I went to high school and middle school and elementary school together. We grew up in the same very tiny town in New Jersey.
New Jersey.
And
And as we realized, Yuko is the Kevin Bacon of webcomics.
she basically is. But I'm, in that analogy, if Yuko's the Kevin Bacon of webcomics, then I'm a truck driver. Like I'm not an actor in that analogy at all. But yeah, so I know Yuko. And
do you know all those other people? Do you know like George Rohack and no? Oh, okay.
No,
never mind.
What happened is I called up Yuko a few weeks back and said, "Hey, I'm going to be in New York City in October," and she said, "Oh, great, let's hang out." And we did, and I met Conrad and some of her other friends. And when I did, Conrad said, "Hey, you should be in podcasts."
Was he drunk at the time?
He was not drunk. He
Whoa.
might have been high on life.
When is he not high on life?
I mean, he's basically always high on life is my impression. But I mean, we had a good time. We hung out for an afternoon. And then he said, "You should be in podcasts. I have friends who do podcasts. When are you going to be in the city again?" And I
You
said,
do have him instead of the money.
pretty much. Yeah. I mean, I actually did apply to become an astronaut.
Really?
Yes.
Don't you
No,
also have to be like a fighter pilot or
Well,
something?
so there's
or-
the military track, but there's also the civilian track. And so they sent out a solicitation for applications, 9 months ago. And I looked at it and I said, okay, so I obviously don't meet the military track, but civilian track, check. Yeah, okay, I have the degrees and prerequisites. I can apply for this.
Yeah, but
So
I guess that didn't work.
No,
though.
it didn't work. I'm not in space right now.
Yeah.
But what I really want from that actually is the rejection letter. Because, how does every rejection letter start, right? It starts with, "Dear Dr. Becker, we were very impressed with your qualifications, blah, 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 blah. And we felt that you were very, you were very well qualified for the position, but we found other people that suited our needs better. And so what I'm going to do is I'm going to take that letter, highlight the part that says you were very qualified for the position, and then frame it and say, see, NASA says that I am very well qualified to be an astronaut. I have it on NASA letterhead."
Well, one day when they make like a documentary about you, right, and for the local news, for whatever reason it's going to be, which we can't guess yet, right? They'll have that letter will be part of the thing, like, oh, rejected as an astronaut, but succeeded at this other awesome thing. Stupid NASA turned this guy down. They didn't know better.
Or it could be rejected as an astronaut and then the explosions.
Yes. Well, no, the explosions already happened. That would be a show about what I did in college. But, yeah, so I am a freelance astrophysicist. So
you're clearly way smarter than we are.
You have a pretty good radio voice despite just talking in your normal voice.
Thank you. Yeah.
I don't have to close mic you or anything weird.
That's awesome. Anyway, yeah. So he said you should contact them the next time you're in town. And I said, well, I'm in town next month.
And you actually did that? I
Well-
mean, a lot of times we'll meet people at conventions, we'll meet, all right, and we'll say, oh, you should do this, you should do that, but none of those things ever actually happen.
Right. So I'm a freelance astrophysicist. If I don't actually meet people, then I don't have a job.
Oh, okay.
Yeah.
Well, I'm sorry. I wish I could hire you for something.
No, don't worry about it. That's
but
not
maybe
what it's
somebody
about.
listening out there needs
It's
an
not about me.
astrophysicist.
It's not about me. It's about the science.
So let's talk about the science. So you're an astrophysicist, right?
Yeah.
I think the email though said you were a computational cosmologist.
Yes.
Right. So.
Yes.
And I guess there's also astronomer. So, I sort of know the difference between those three things.
Okay, so so the story here is there's astronomy, there's astrophysics, there's cosmology.
Is there anything else I'm missing? Is there another one?
I mean, there's
Astrology.
yeah,
That doesn't
so
count.
I was going to get to astrology in a moment.
We're well aware.
Yeah, so the general story is if you think that stars are small to medium-sized objects and that galaxies, hundreds of thousands of light years across, or tens of thousands of light years across, are very big objects, then you're probably an astronomer or an astrophysicist. Whereas if you think that galaxies are very tiny, maybe point-sized objects, and the universe is very large, then you are probably a cosmologist. But the lines are fuzzy, and it's not wrong to call anybody in any of those fields an astrophysicist, because that's sort of a blanket term. And the other thing is, outside of, academia and conferences and whatnot, anyone who's an astronomer or a cosmologist or an astrophysicist usually self-identifies as an astrophysicist, because if you say that you're an astronomer, people will think you're an astrologer and ask you about their horoscope.
Oh, I mean, non-science people will think that.
Well, but if you say that you're a cosmologist, people will think you're a cosmetologist and start asking you about makeup.
Oh, okay.
I was going to make a joke about Cosmo.
Yeah, I mean, don't. Goodness, that's so
See,
clever.
I was thinking, if you were saying this, I was assuming that you were going to identify yourself to a smart person and that you would say astrophysicist because that's more impressive, right? We tend to look at like the biggest people in science are astrophysicists, like the Stephen Hawkings and that, right? So if you were just like an astronomer, that sort of, I guess, seems like a not as prestigious word.
It's got physicist right there in the word, which leads to a lot less confusion. I guess it makes it sound more impressive, but mostly it's that if you say astrophysicist, people know that you are working with a lot of math and not with horoscopes.
Okay, so let's talk about the computational part of this.
Right. So basically what I
That's what we know about that.
Sure,
That's
yeah.
the part we know.
So in my research, what I do is
It's Monday, November 19th, 2012. I'm Rim.
I'm Scott.
And this is Geeknights. Tonight, we have a guest on the show who would probably like to introduce himself.
Hi, I'm Adam Becker, and I'm a freelance astrophysicist.
That is probably one of the more badass job titles I've ever heard.
Well, thank you. I made it up, so...
Let's do this. So, some of our listeners may know a person named Conrad who has been on the show once or twice before.
He's a character in Johnny Wander, and he's also a real person.
He is a real person.
I knew him when he looked like an 11-year-old boy.
I knew him when he was wearing a safety bucket that was dressed as Naruto.
Yes, he was inside of one of those highway safety barrels that itself was dressed up as Naruto.
But anyway, you might be wondering why we're talking about Conrad. You might think he's here. He's not here. Instead, he has sent a friend of his, a friend named Adam. What's up, Adam?
Hey, how's it going?
So we met Adam 15 minutes ago, maybe, and
We've done nothing but talk about embarrassing Conrad stories and teeth.
It's true.
So Adam seems pretty awesome, and we are going to do a show with him right now. So, Adam, why is it, for our listeners, I mean, I already know, why is it that you are so awesome and we would want you on the show?
I'm just a pretty cool guy, but I suspect that it has more to do with the fact that I am a freelance astrophysicist.
Wait. So when you were choosing a job back in the day, you decided to go for the dream.